Hey guys, today we're going to be starting Unit 2, and this unit is comprised of Chapter 5, which we'll be starting today, and then Chapter 6, which I know is not in order. We just did Chapters 1 and 2 in Unit 1, and now we're going to be doing 5 and 6. We're going to come back to 3 and 4 in the next unit. So this unit is all about this chapter is about linear relations. Chapter 5 is all about linear relations, and then Chapter 6 is about polynomials. This unit, Unit 2, is probably the most important unit by far in terms of what you need to know for grade 10. It's not going to be like the only unit on your PAT, obviously, so it's important to know everything that we do this year. But this unit is the one that if don't have a good understanding of this unit, you're going to really struggle in grade 10. So make sure that if you are struggling with this stuff, you get lots of extra help. Anyway, let's get into it. Okay, so this is lesson 5.1, describing relations algebraically. First, just some definitions. The independent variable is whichever variable is on the x-axis. The dependent variable will be found on the y-axis. And when it comes to identifying whether a variable is independent or dependent in like a word problem per se, the dependent variable will always change depending on the independent variable, and then the independent variable changes on its own. These are the two equations that we use for linear relations. It's called the slope-intercept equation. This is the most common version of the equation, y equals mx plus b, though you will also sometimes see it where the mx and the b have just swapped places. What all of that means, so the x is just the independent variable, the y is the dependent variable, the m is the rate of change, which is the change in y divided by the change in x. And then the b is what the y value is when the x value is 0. It's also sometimes referred to as the initial amount because it is the amount of y before the x value starts. And on a graph, it is the y-intercept. So sometimes b is just referred to as the y-intercept. So what we're going to be doing in today's lesson is essentially just going through how to write these linear equations in the form y equals mx plus b, based on whether you're given a graph or a table or a diagram or a word problem. So you do always want to start by finding the slope and the y-intercept. Those will often need to be calculated. And then you plug them into the equation, so the y equals mx plus b. In your final equation, the x and the y stay as variables. So they stay as x and y. Just the m and the b values should be replaced with numbers. So let's look through a couple different examples of this. Okay, so we're going to start by having a table given to us and trying to write our equation of a line from that. So the first step is going to be to find the rates of change for both our x and our y. So we're going to call that delta x. Anytime you see a triangle like this, it just means a change in, or the rate of change. So this is the rate of change for x. On the other side, we'll also find the rate of change for y. And the way we do that is just see how much these numbers are going up or down by. So the rate of change for x, we would do 7 minus 5 is 2, 5 minus 3 is 2, and 3 minus 1 is 2. So we just start at the bottom and then subtract the number immediately above it. That is our rate of change. So the rate of change for x is 2 all the way down. And then we'll do the same for our y values. So 8.7 minus 7.2 is 1.5. 7.2 minus 5.7 is 1.5. And 5.7 minus 4.2 is 1.5. Now, the reason we check it the entire way down is because if it is not the same the whole way down like this, if it's, for instance, the same on one side but not on the other, it means that you're dealing with something that's not linear. And so you would have to be able to identify that. So anyway, that is step one to find our change in x and our change in y. Step two is going to be to use that to calculate our rate of change, which is our m value. So what we're going to do now is say that our m value is equal to our change in y over our change in x. So that's going to be 1.5 divided by 2, which is 0.75, or, oops, not 1/4, 3/4. From there, we are going to calculate our b value. And in order to do that, we are going to start with our equation of y equals mx plus b. We're then going to plug in the m value that we just solved for. We're also going to plug in any of our x, y coordinates from the table and solve for b. So plug in our rate of change and any x, y coordinate. So what that would look like, I might just pick this first coordinate, but you can pick any pair of numbers that go together. So our y would be 4.2, our m is 0.75, our x is 1, and then I just need to solve for b. So 0.75 times 1 is obviously just 0.75. And then to move the 0.75 away from the b in order to isolate the b, because the 0.75 is positive, I am going to subtract 0.75. That cancels out. What I do to that side, I must also do to the other. And 4.2 minus 0.75 gives me 3.45. And then our final step is to go back to our y equals mx plus b and just plug in our m value of either 0.75 or 3/4 and our b value. And that would be our final answer. Okay, so we started off up at the table. Step one, finding our change in x and our change in y. Step two was calculating our slope, or sorry, our rate of change, our m value. Step three was plugging in a coordinate and our m value in order to solve for b. And then our last step is to just plug in our m value and our b value into the y equals mx plus b equation. Okay, for the second example here, we're going to be dealing with a word problem. So it says, I brought $400 shopping and spent $20 on each dress I bought. Write the equation to show the money I have left relative to the number of dresses I bought. So you don't know how many dresses I bought. You also don't know how much money I ended up with. So you're just going to be writing the equation for this. You can't actually solve anything. So what we need to do is we need to identify what is our rate of change, what are our two variables, and what is the initial amount. So we'll start by looking at what were our two variables. Okay, so we'll start by identifying our independent and our dependent variables. So these are the two things that we don't know. Again, we don't know how much money I spent. That's one of the things that we're looking for. The money I have left. And we don't know the number of dresses I bought. And yet those are the two things you should be comparing in this equation. So you have to figure out which one of these depends on the other one. Well, the amount of money I have left depends on how many dresses I buy. The more dresses I buy, the less money I'm going to have left. So knowing that, my independent variable is going to be the number of dresses. And I might represent that with a D, or you could represent it with an X. And then my dependent variable is going to be the amount of money I have left, which you can represent with like a Y or an M for money, whatever you want, okay? Then we also have to identify our rate of change and our initial amount. So our rate of change is like that M value in Y equals MX plus B. The initial amount is our B value. So the rate of change is how much this is going to be changing by. Well, every time I buy a dress, my amount of money changes by $20. So my rate of change is going to be that $20. And then the initial amount is how much of my Y value, which is my money, how much of that I had before we started with our X. So before I started buying dresses, how much money did I have? Well, that would be the $400 I brought with me to go shopping. So now that we know all of that, our equation is just going to be something along the lines of Y equals our rate of change X plus the 400. Now, the one thing you do need to watch out for is should there be any negative signs? And because I am spending or losing $20 every time I buy a dress, my rate of change actually needs to be negative. My amount is going down. So Y equals negative 20X plus 400, or you could have that the money is negative 20 times the number of dresses plus 400. It doesn't really matter what you use for the variables as long as you have identified what they mean and then have your rate of change and your initial value correct. So either of those could be a correct answer. Okay, the third example that we're going to look at is how we write the equation if we're given a picture. So the first thing I'm going to do is identify my variables. So I'm going to say that X is my figure number and Y is my number of dots. So essentially I'm saying these are my X's, these are my Y's. Now that I have that, I'm going to go on and find my rate of change. So step one, we have identified our variables. That's what we did right here. Step two, find our change in X and our change in Y. So for our x's, 3 minus 2 is 1, 2 minus 3 is 1, therefore our change in x is 1. And for our y's, we have 7 minus 5 is 2, and 5 minus 3, which is 2. Now we go on to step 3, which is calculate our m value, or our rate of change. So m is equal to a change in y over a change in x. Our change in y is 2 divided by 1, which is just 2. Now we have to calculate our b value, which, just like in the first example that we did, we're going to start with y equals mx plus b. We're then going to plug in our m value and any pair of x and y terms. So I'm going to pick an x value of 1, which means my y value is 3. This is the pair that I'm dealing with here. So 3 equals 2 times 1 plus b. So 3 equals 2 plus b. And then, of course, I need to move my 2 to the other side because it is a positive number. I will subtract it to cancel it out. And then that means I must also subtract on the other side, which means that my b value is 1. And then, of course, my last step is to just write the equation. So y equals my m value of 2x and then plus 1. And that would be my final answer. Okay, if you are given a graph, this is actually the easiest way to write the equation of a line. And that is because our m value is just the rise over the run. So the rise is how far up or down we go. The run is how far we go from left to right. You always read a line the same way you would read a sentence, starting from the left, going towards the right. And then our b value is just the y-intercept, which is where our line hits the y-axis. So we'll start by figuring out what our slope is. So a rise over run, all we're going to do is pick 2 points that are next to each other. It can be any 2 points. I'm going to pick these 2 just for simplicity's sake because they're nice and easy to see. And then our rise, as we're moving from left to right, is how far up or down we have to go to get from this point to this point. So in order to do that, I need to go down. So that is my rise. And I've gone from 15 down to 10. So I have gone down by 5. In order to show that it's down as opposed to up, we represent that as a -5. So our rise is -5. And then our run is how far from left to right we have to go. Your run should always be positive. Your rise can be either positive or negative. That will be true as long as you're reading the line in the correct direction. So here we've gone from 1 to 2, so we've just gone over 1. So our run is 1. -5 over 1 is just -5. So our m value, or our rate of change, is going to be -5. And then our y-intercept is just where this line hits the y-axis. So it would be right here, which means that our b value is 20. Knowing that, we just plug in our m value and our b value into y equals mx plus b, and that's our final answer. Okay, the last thing that we're going to do today is go over how to actually solve a linear relation. So step one will be to write the linear equation, which is what we've been doing so far this lesson. Then you're going to be given either the independent or dependent value. So plug that into your equation where either the x or the y is, depending on which value you were given, and then isolate the other variable. Okay, so let's go through this example here. A hot air balloon was 62 meters high when it started descending by 12 meters every minute. How long did it take for the balloon to be 15.5 meters high? So we're going to start just like we did with our previous word problem by identifying the different parts. So we have our independent variable, our dependent variable, our rate of change, and our initial value. So the easiest things might be to identify our initial value and our rate of change. Our initial value is the height it started at, so that would be the 62 meters. So our initial amount is 62 meters. Then it started to descend by 12 meters every minute. So it's going down 12 meters every minute. That is our rate of change, is the 12 meters per minute. And because it's going down, we're going to make it negative. And then our two variables, the two things that we're comparing, is how long it took, so time, and the height. The height that the balloon is at depends on how long it's been dropping for. Also, a little hint, anytime time is one of your variables, time is always independent. So time is our independent. You can call it X or you can call it T, whatever you want. And then our dependent variable is going to be the height of the balloon, which you can call Y or H or whatever you want. So now that we know that, we can write our equation. So you can write it as Y equals negative 12x plus 62, or maybe H equals negative 12t plus 62, whichever one you would rather. Now that we have our equation, our second step is to plug in the value that we were given, that is either x or y. So we were given 15.5 meters and asked for the time. So we've already said that this is our height, and height is dependent. So we can plug in our 15.5. And again, you could be plugging it in where the y is instead if you'd rather use this equation. And then we have to isolate for t, or our x. And so, as we learned in the first unit, we start by moving whatever's furthest away from it. So we're going to move the 62 first because it is positive 62. We subtract 62. 15.5 minus 62 is negative 46.5. That is equal to the negative 12t on the other side. And then, of course, we need to move the negative 12 away from the t. We divide to do that. And that gives us 3.875 minutes as our t value. So that would be our final answer. You could round it to 3.9 minutes if you'd like. Okay, that is it for today's lesson. I know it was a long one, but it was an important one. Anyway, let me know if you have any questions.